Hey everyone, hi, this is Ankush, and in this video, we'll be looking at the basics of binary number systems. Why are they used in computers, and why do they find their use case extensively in computer science? Okay, so without any delay, let's just dive deep into it. Okay, so before we deep dive into binary number system, we should understand what is a number system, right? So just like we have like different languages which we speak and read and write, in different languages, the way we read, the way we write is different, right? They have different grammar, they have different symbols to represent characters and letters and everything, right? Similarly, a number system is a different way, or number system basically rolls out the rules to represent numbers in that particular number system, right? We have different number systems like the Roman number system or the decimal number system. Idea is to represent numbers, but the rules, the symbols, they change, right? So over the human history, we have used different number systems, decimal number system, binary number systems, and some very ancient ones, some of which you can see in the image below, right? Even like let's say in Hindi we have a different way to represent numbers. In English we represent it differently. In Roman number system we represent it differently. But the basic idea remains the same, that it is just a different way to represent numbers. Okay. Now, just like decimal number system and the Roman number system that we just spoke about, binary number system is also just a way of representing numbers. Now, why is it used in computers, and why does it find its use so extensively in computer science? That is something that we'll try to answer in this video. Okay. So now, one of the most popular number system that we probably use in our day-to-day lives as well is the decimal number system, right? Now, in decimal number system, we have where each digit can have basically 10 different meanings. It can be a zero, it can be one, it can be two, three, four, five, six, seven, eight, nine. Whatever numbers we see are a combination of these 10 numbers, right? We use different combinations of it to represent different numbers, right? So for every digit, it can represent 10 different, it can have 10 different meanings, right? It can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever it is. Now, so first of all, let's try to understand how decimal number system works, because the way the number systems work is exactly similar in different number systems, just the notations and the symbols change. So in decimal number systems, as we spoke about, we have 10 different options to each digit can have 10 different meanings. So let's say, how does a number 23 represents? So each number in a decimal number system is multiplied by a power of 10, so that finally we add all those numbers and get a cumulative sum which represents the number itself, right? So the rightmost number is multiplied by 10 raised to the power 0. Then the number next to it, as we go along towards the left side, the power of 10 keeps on increasing. So in this case, 3 is the rightmost element, what we normally call the ones place. So it is multiplied by 10 raised to the power 0. Then we go on to towards the left side, where we have 2, which is multiplied by 10 raised to the power 1. If there would have been another number, let's say 123, then that 1 would have been multiplied by 10 raised to the power 2. If another number would have been there, it would have been multiplied by 10 to the power 3, and so on. So this is how we generate numbers in our decimal number system, right? We start from the rightmost number, that is multiplied by 10 raised to the power 0, and then we move along 10 raised to the power 1, 10 to the power 2, and so on. And why do we multiply by powers of 10? The reason being that every number can have 10 different digits, can have 10 different meanings. Now, when we come to the binary number system, a binary number system, just as the name suggests, has only two options: a 0 or 1. That's it. We can for every position that you have in your number, you can have only two options. You can either put up a 0 or 1. You just have two options. But just because you have two options, that does not limit you from representing numbers. You can still represent numbers using the same exact logic. So let's see how we can represent the number 23 using ones and zeros only. That is how we can represent the number 23 in a binary number system. So let's look into it. So if you see here, we have 10111, which is the binary notation for the number 23. But how is it? Let's look into it. Now, just like we had in decimal number systems, we were multiplying with powers of 10. Now, because we have two options, we are multiplying with powers of 2. The rest of the logic remains the same. The rightmost element is multiplied by 2 raised to the power of 0. And as we move along towards the left side, powers of 2 keep on increasing, right? And 1 and 0 basically, you just multiply by 1 and 0, you get the answer. So in this case, 1, 0, 1, 1, 1, 1 into 2 raised to power 0, which is the rightmost element, gives us the number 1. Then 1 into 2 raised to power 1 gives us 2, because 2 raised to power 1 is 2, and then multiplied by 1 is 2. Then 2 raised to power 2 is 4, multiplied by 1, again 4. Now 2 raised to power 3 is 8, right? But it is multiplied by 0, so 0 will be added. Now 2 raised to the power 4 is 16, multiplied by 1 is 16. So let's add everything up. 16 plus 0 plus 4 plus 2 plus 1 gives us the number 23, right? So that's how we represent numbers in binary. Again, the basic logic remains the same. How do we represent numbers? But just instead of multiplying with powers of 10, we multiply with power of 2, right? Because we have two different options, either a 0 or 1, right? But now a very interesting question comes up. Why is it used in computer science, or why is it used in computers? Now, for this, we have to understand how does a computer work. A computer is made up of millions of tiny switches known as transistors, right? Now, a transistors, they have basically two states. They can be either on or off. Now, just because the computer is made up of millions of transistors, everything revolves around switching these transistors on or off based on our use case. That's why it makes sense to have only two options to represent our positions, because all these numbers are just trying to depict or represent the state of the transistor, which can be either on or off, right? So in this image, you can see transistors, which can be either just on and off. And that's why, because a computer is made up of these transistors, we use binary numbers in computers. Okay. So, but it still is a bit of an abstract thing. Still very abstract. How does computers use these binary numbers to represent or store values? Let's say store text. Let's say if I get a message hi, or if I type hi on my computer, how is it stored in the computer's memory? It's because right now we are just saying that everything is revolving around transistors, but it's a text, right? Hi is a text. How does it stores in how is it stored in the computer? The answer is the computer uses the same binary number system. But how? Let's look into it. So now storing text in computers, if you look at it, it is just that we have to give every character a number such that that same number can be represented in binary format and stored. And that is where the ASCII format comes in. Now, the full form of ASCII is American Standard Code for Information Interchange. But if you just look at it, it is just basically a bunch of people coming together and finalizing that to represent this character, we'll use this number. That's it. They just map characters and numbers so that it becomes easy for us to store those characters with the help of numbers. So that is where ASCII comes in, and that is how text is stored in computers. So still, let's dive deep into this bit and understand how does it happen. So first of all, we should understand that in computers, the binary numbers that we talk about, such as in decimal number system, which we call individual numbers as digits. In binary numbers, we call individual numbers or individual digits as bits, right? But now one bit at a time is not much of a help here, right? So that's why 8 bits combined together are used to represent some kind of information. Now 8 bits together, they form 1 byte, right? 8 bits together, they form 1 byte. Again, why 8 bits are combined as 1 byte? Because one bit alone cannot represent a lot of information, right? It just represents the state of one transistor, either on or off, right? And just as you saw with number 23, when we're trying to represent it, we still needed 5 bits. So one bit alone does not have a lot of options. One bit alone can have only two options, 0 or 1, right? So it can either represent the number 0 or 1, nothing else. 2 bits together, they can represent, because we have four possible combinations, 0 0 0 1 1 0 1 1. It can represent 0 1 2 3. right? Similarly, when we have three bits, it can represent seven numbers, 0, 1, 2, 3, 4, 5, 6, 7. That's why, the more number of bits, the more numbers we can represent. So with 8 bits, we can represent 256 numbers, starting from 0, going to 255, because that is the total number of combinations that we have. And those 256 numbers can be used, they can give us a decent amount of information. That's why whenever we are transferring information or storing information, we make use of a byte instead of a bit. So 8 bits together, they're combined and they're used as byte. Now, coming back to the original question, how are characters stored with the help of ASCII numbers? Just as we spoke about, we just gave some number mapped to a particular character. So capital A was given a number 65, small a was given a number 27, and the exclamatory mark was given a number 33, such that everything that you do in text, like in English text, either let's say uh, capital letters, punctuation, small letters, whatever it is, they are given some specific values such that they can be stored. Now, whenever a computer has to send you a message, let's say, hi, it can send you with the help of binary digits, right? Binary digits combined together, 8 bits together combined to form byte, such that the first one forms the number 72, which is the ASCII code for H. The second one forms the number 73, which is the ASCII code for I. And the third one forms the exclamatory mark, which is number 33, which is the ASCII code for I. Now, this is how numbers are stored in binary, right? So whenever you're getting a message hi, you're just getting a bunch of binary numbers or bytes combined together, you know, and the computer understands that, if it's getting the number 72, it has to, it has to represent H. If it is getting 73, it has to represent I. If it is getting 53, it has to represent the exclamatory mark. So that combined together, it makes the message hi. In fact, everything that you see on a computer screen is just a combination of zeros and ones. Because that is exactly what a computer does. It stores data in the form of zeros and ones, right? In fact, the emoticon, or one of your favorite emojis that we use quite a bit, has the what we call the binary representation as this. This is the binary representation of our favorite emoticon, as we call it, laughing tears with joy. That is basically this binary number. So whenever you are transferring an emoticon, you're just basically transferring this binary digit code to someone else, right? Okay. But we don't generally don't only just store text in our computer. We don't only send text, we send videos, we send images. What about those? What about those? So how do we handle images and videos? Again, since we spoke about a computer can only deal with binary numbers. So again, images and videos, they're also just binary numbers sent around. That's it. So now how do we come up with binary numbers? How we can represent images and videos. So just as we had ASCII numbers for text, we have, you know, representations for colors, right? Because every image is just different colors combined together, right? Images basically different colors combined together. Some might be, bit heavy and everything. So there are different color combinations and different color codes available. But one of the most popular one is RGB. It stands for red, green, and blue. This basically indicates how much red is there in your color, your image, how much green is there, how much blue is there, right? So we use 3 bytes. That means we have 24 bits, and each of these bytes represent how much red is there, how much green is there, how much blue is there, right? Just a combination of these, and we'll get what we want. Now, for example, in this case, the first bit or the first byte, as I should say, which is the set of 8 bits, represents the amount of red. The second one, the second set of 8 bits, that is the second byte, represents the amount of green, while the third one represents the amount of blue. Now, each of these combinations can have 256 different combinations. So using these 3 bytes, we can represent millions of numbers, millions of colors, sorry, millions of colors, which is exactly what we want. Again, there are different combinations, different protocols or different rules available, but one of the most popular ones is RGB, right? So just as we spoke about, the first byte represents the amount of red, the second byte represents the amount of green, oh sorry, blue, and the third byte represents the amount of green. Now, one more important question that can come up in your mind is how does the computer identify that it should perceive this as a color or should it perceive this as a text? Very obvious question because the same number, this is exactly the same number that was being used to send a text message as hi. So where does that distinction come in? That is a good question to ask, right? That's a very valid question. That is something that should be asked. That is where the file extensions that we see come into the picture. Let's say you send across a file which is a text file or a JPEG file. Now, whenever a computer sees a text file, it knows that the binary codes or the bytes that it has, they represent text. They represent, so this particular byte that we just saw represents H and not red. But if it is the extension of the file is .jpeg, which is basically the file extension for images, it knows that that particular byte represents red, the amount of red, right? In fact, the code that you just see on your screen represents a very beautiful color. I won't say exactly my favorite, but one of the good colors, which is this, a shade of yellow, something, I don't know, more of a green, but something like this. So basically this represents this one. Again, that is where file extensions come in very handy. A text file generally tells our, no, generally not, specifically tells a computer that you have to perceive this as a text. So whatever binary codes, whatever bytes you're seeing this, use them as text, map them to their particular ASCII values, and get the answers, right? Okay. Now you might be saying that in our computer we can just not store English characters. We can still have characters in Hindi, Arabic, and so on. For that, a different kind of encoding or a different kind of set of rules is being used, known as Unicode, such that for every character we use 2 bytes. Now here to represent a single character, 1 byte, that is a set of 8 bits, 8 bits is enough. But for Unicode, generally we use 2 bytes to represent a particular character. Okay, I hope you find this interesting. Now, one more thing about this is that everything that you see on the internet that is being transferred is around bytes. So different kinds of what you say symbols have been come up to represent a group of bytes, or just like 100 and 1000, we have different milestones around those. We have similar things around bytes as well, such that 1 kilobyte is around 1000 bytes, 1 megabyte is around a million bytes, 1 gigabyte is around a billion bytes, and 1 terabyte is around a trillion bytes, right? So next time, whenever you are transferring a movie to your phone and it says 750 MB, you know that you are transferring around 1 into 750 million bytes, right? So uh, this was about binary numbers in general and how do they work in the computer memory, right? Again, okay. Now, since we have this information that how much each character takes to store or how much each, how basically what are bits and bytes, since we have that information, we can use that to identify how does memory management in computers happen. So let's say if you are storing a character in your memory, it just takes 1 byte. Now, why am I saying this as 1 byte? Is let's say when you're storing a character, you're basically storing a number between 0 to 255. You're basically storing the ASCII value of it. So as we just saw that when you have to store the ASCII value of it, you need 8 bits. That is, you need 1 byte, right? So whenever you're storing a character, you're basically storing 1 byte of memory. You're basically using 1 byte of memory. But let's say you're storing a number. Now a number can be bigger than 255. Let's say you're representing 10,000, you're representing 1 lakh. So a number like that, 10 power 5, 10 power 6, you're representing numbers like that. So in that case, 8 bits are not going to be sufficient, right? Because we just saw it, right? With 8 bits, you can have 2 raised to the power 8 different combinations. So you can only represent numbers till that point. But let's say if you want to, represent, or if you want to store bigger numbers, then you need more bits, more bytes, right? That's why generally in computers we use 4 bytes, which is 32 bits, so that we have 2 raised to the power 32 different combinations, and we use them to represent numbers, right? Let's say, for example, you a message is sent to you. Let's say on WhatsApp, you receive a message called as "Hey there." Now, when you receive a message like this, you know exactly how much memory is required. Let's say when you look at "Hey there," you are basically storing how many characters? HEY, 3 characters. Then a space, which is counted as a separate character. It has a specific ASCII value associated with it, so that should be counted as a different character. So these are 4 characters. Then THERE, which is again 5 characters. So that makes 9 characters, and then exclamatory mark. So these are 10 characters. So when you're being sent "Hey there," you're basically being sent how much amount of data? You're basically being sent 10 characters. That means 10 into 1 byte. Each character takes 1 byte. You're basically being sent 10 bytes of data. That means 80 bits of data is being sent to you, right? So you know exactly how much amount of data is being sent. Let's say you have to store 10 numbers in your memory. You have to store 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 numbers in your memory. If you have to store 10 numbers in your memory, each number takes 4 bytes. So 10 numbers will be taking 40 bytes, or 40 into 32 bits, right? So now whenever you look at a text message, whenever you look at a number, you know exactly how much amount of memory it is taking. So and now next time when you look into the settings of your phone and you go into memory, into storage, and let's say it says that you have 23 MB worth of messages, you know exactly how many characters are there, right? So this knowledge comes in particularly handy when you when you involve software development, because a lot of times in software development we have to store data, we have to manipulate data, we have to use data according to our use case, right? And this information comes in really handy, right? Let's say when you're storing a character, that means you're storing a byte, you're storing 8 bits, so you will plan that accordingly, right? When you're storing a number, you need 4 bytes, you need 32 bits, right? Also, so this information comes in very handy when you're involved in software development. So again, if you plan a future in software development, this is an information that is very useful for you, something that you should look into very seriously, and this will ease out your life a lot more. Particularly useful, right? Let's say if you want to represent a decimal number, let's say 1 point something something something, right? In that case, do you think 4 bytes will be enough? Okay, that's the question. This is where we leave, right? It's a good question for you to leave at, and then you can research on it on your own. But again, this is exactly the things that we wanted to cover in this one. Again, we understood what are binary numbers, how are they useful in computer science, and how they find their use case here. And thank you very much for watching the video. I hope you had some fun. Thank you, guys.